Most beekeepers are trapped in the dogma that a larger bee colony automatically requires gigantic space. For decades, an unfounded tradition has dictated working with 2 or 3 brood boxes. The result is beekeepers breaking their backs lifting hundreds of kilograms of unnecessary weight, while high honey yields stubbornly fail to appear. Why? Because they ignore basic biology and mathematics. Have you ever asked yourself what truly dictates a colony's need for space? Are you raising bees, or are you raising empty space? The maximum biological capacity of a top-quality queen is exactly 2,000 to 2,500 eggs per day. Considering that the ontogenesis of a worker bee lasts exactly 21 days, at the absolute peak of the season, the queen requires a maximum of 45,000 to 50,000 worker cells to maintain a continuous brood cycle. Those 50,000 cells fit precisely into a single standard brood box. Every additional cubic centimeter of space beyond that is not space for brood, but space for storing and wasting resources. Welcome to the brutal deconstruction of beekeeping myths. Today, using the language of physics, economics, and biology, we demonstrate why single brood chamber beekeeping is the superior model for maximum production and reduced operational costs. To optimize production, we must analyze the spatial architecture of the nest with surgical precision. Bees naturally strive to form a compact, spherical brood structure. The geometry of a sphere provides the smallest surface area relative to volume, guaranteeing minimal heat loss. That is the law of thermodynamics. In the traditional system with 2 brood boxes, the queen physically gets lost in the enormous volume. She lays in an elliptical pattern, moving from the lower to the upper box. This transition directly disrupts the continuity of thermal mass. Worker bees become scattered across too large an area, and maintaining the microclimatic conditions of 34.5 to 35 degrees Celsius becomes energetically too expensive for the colony. In a single brood chamber, the queen is forced to operate exactly as she is genetically programmed, radially, from the center toward the periphery. She maximizes every available cell before moving to the next frame. The result is brood frames filled from bar to bar. The concentration of young bees on such dense brood creates a powerful biological unit. The efficiency of vitellogenin protein distribution increases, and the immunity of the entire colony grows exponentially due to reduced energy consumption for heating excess air. Science confirms this precisely. A study by Ovinje and Hoover, published in 2018 in the Journal of Economic Entomology, provides concrete field data. They compared 100 colonies in a single brood chamber with 100 colonies in 2 brood chambers during canola pollination. The numbers do not lie. There was no statistically significant difference in the total number of adult bees. Moreover, single brood colonies had more capped brood per frame than double brood colonies. In a compact space, the queen is simply more efficient. When observing labor efficiency, single brood colonies produced more pollen and nectar foragers. A smaller but extremely focused group of bees in a compact space mobilizes a much larger percentage of its population for fieldwork, while massive colonies lose efficiency in internal logistics and heating unnecessary space. Honey yield per frame and overall return on investment have been proven to be higher in a single brood system. The most common argument amateurs raise against a single brood chamber is, if I reduce their space, they will immediately enter the swarming impulse. This is a fundamental misunderstanding of cause and effect relationships inside the hive. Swarming does not occur exclusively because of reduced brood space. Swarming occurs due to resource congestion and pheromonal deficit. Let us analyze pheromonal saturation. The queen releases queen substance that spreads throughout the colony through food exchange and physical contact. In the enormous volume of 2 or 3 brood boxes, the concentration of this pheromone at the edges of the nest rapidly declines. Bees on the periphery receive a chemical signal that the queen is weak and that her presence is fading. The colony's brain then activates the alarm for swarming. In contrast, in a compact single brood chamber, pheromonal saturation is absolute. Radial distribution of pheromones is fast and flawless. Every individual clearly detects the presence of the queen, drastically reducing the impulse for division. Where exactly does the mistake occur among beekeepers who attempt a single brood chamber and experience collapse through mass swarming? The mistake lies in inadequate management of the honey cap. The honey cap is the band of honey beneath the top bars that acts as a physical barrier. Bees instinctively tend to deposit food directly above the brood. If you allow this band to become too thick, it moves downward and compresses the available space. The queen feels blocked. Space for egg-laying disappears, and young nurse bees are left without open cells. To prevent this, you must apply the mechanics of early expansion. The honey super in this system becomes the main regulator of space. You do not wait for the main nectar flow. Honey supers above the queen excluder are added early, already during the spring nectar intake. This move creates a vacuum of space above the nest. If you notice a honey band blocking the queen, physically damage the cappings with a hive tool or beekeeper's knife. Instinct forces the bees to repair and relocate the damaged honey. With a large empty super above their heads, they will transport it through the excluder upward, freeing cells in the brood chamber. By constantly adding foundation frames in the supers, you force young wax-producing bees to spend their energy building new comb, preventing them from directing that energy toward drawing queen cells below in the brood chamber. With this method, you achieve surgical separation inside the hive. The lower floor, the brood chamber, becomes a hyper-focused biological factory where every calorie is spent incubating new generations. The upper floors become strictly honey storage. There is no mixing of resources and brood nest. During intense acacia nectar flows, in a two-brood system, the first 15 to 20 kilograms of incoming nectar are deposited around the brood, in the upper brood chamber. For you as a beekeeper, that honey is lost because it is mixed with brood and cannot be extracted. In a single brood system, this buffer space is biologically eliminated. The forager lands at the entrance, enters the hive, and encounters a brood chamber completely filled from wall to wall with worker brood. There is physically no place to store honey on the ground floor. The bee has no other option but to pass through the excluder and deposit nectar directly into your honey supers. Every drop of nectar goes directly into your extractors, increasing your total profit. Finally, we reach the hardest myth, the fear of winter mortality. Critics claim that bees will die massively of starvation in only one brood box. Physics proves the opposite. Wintering in a single brood chamber maximizes thermal efficiency. Winter bees, with developed fat bodies rich in vitellogenin, form a dense winter cluster. They do not need to burn enormous quantities of expensive honey to heat a massive empty volume in a lower or upper brood chamber, as they do in double systems. A standard brood box holds 10 frames. In our climatic zones, bees need 15 to 18 kilograms of quality food to overwinter successfully. This amount of carbohydrates perfectly fits into 6 to 7 frames filled with stores, leaving the central, partially empty frames as space for the formation of the cluster core. Less empty space above the bees means fewer heat losses. Less heat loss means lower food consumption. Lower food consumption results in reduced stress on the bee's hindgut, eliminating the risk of dysentery. The final outcome is a healthier colony and a far more explosive biological start in early spring. An additional benefit of compact space is the direct reduction of treatment costs. Research shows that limiting colonies to a single brood chamber can reduce the average number of Varroa mites by up to 40%, because shorter cycles of mass brood reduce the available space for their reproduction. Treatments with oxalic or formic acid vapors become far more effective. The concentration of the active substance remains high in a smaller volume, penetrating surgically to every individual without chemical waste drifting through empty upper boxes. Your colony remains healthy while consuming significantly fewer treatment resources. Single brood beekeeping is not a hobby, nor merely a change of wooden equipment. It is a redirection of the biological energy of the colony toward your economic goals, under strict respect for thermodynamics. Fewer frames to manipulate, less need for heavy lifting, and significantly higher yields of clean honey. The mathematics of profit is clear, and biology fully supports this transition. If you are ready to work more rationally, optimize costs, and stop being a slave to outdated dogma, this is the right moment to transform your apiary. So that you do not enter this process blindly and make critical mistakes in assessment, I have prepared a detailed and completely free PDF document. It is the Single Brood Chamber Operational Checklist. It contains all mandatory protocols, from the rules for evaluating queen strength before transition to the exact timing for adding the first honey super. The download link for this document is located in the description below the video. Download the checklist and keep it with your beekeeping equipment. If this data-driven analysis brought you real value, follow the channel, leave a like, and share your opinion in the comments. What are your experiences with brood chamber size, and have you already tested this method? This is only the first part. In the next episode of our series, we move to the most difficult beekeeping operation. We will analyze advanced techniques, how to surgically recognize the exact moment when a colony shifts from growth into the swarming impulse, and how to stop that process before you lose 50% of your honey yield. Absolute swarm control is the next level. See you in the next report. Apply science, protect resources.